Hey everyone, and welcome to this explainer. Today we're diving into a literal cosmic detective story. Imagine hunting down some of the most elusive, ancient, and massive objects in the entire universe, supermassive black holes, without ever having to actually leave the comfort of your living room. We're going to break down some recent research that completely flips the script on how astronomers map the cosmos. It takes a historically grueling, time-consuming process and turns it into a remarkably efficient, couch-based discovery pipeline.
So, that brings us to a kind of wild question, right? How exactly do you find a high-redshift black hole from your couch? I mean, space exploration usually conjures up these dramatic images of astronomers spending freezing, sleepless nights on mountaintops, peering through massive telescope lenses. But modern astrophysics is changing, and it's changing fast. As we'll see today, the combination of easily accessible sky survey data and brilliant new satellite tech means that making literal, groundbreaking discoveries about the early universe is now something researchers can pull off right from their laptops.
Okay, so just to set the stage real quick, we are hunting for high-redshift quasars. As you probably know, these are extremely luminous active galactic nuclei, and they're powered by rapidly accreting supermassive black holes. The specific ones we're targeting today are so incredibly distant that their light has been stretching out, or redshifting, for billions of years before it finally reaches us. They are pretty much the ultimate probes for understanding the early universe.
But here's the catch, and it's a big one. It's the ultimate cosmic haystack problem. When astronomers look up, these ultra-luminous, incredibly distant black holes cleverly masquerade as totally ordinary low-mass stars right here in our own Milky Way galaxy. In standard optical broadband images, a quasar billions of light-years away has almost the exact same color and brightness as a common imposter star sitting right next door in our galactic neighborhood. And to make matters worse, these imposter stars outnumber the true quasars by more than 1,000 to 1. For decades, this imposter problem led to immense frustration. Historically, trying to separate the true quasars from the fake stars meant astronomers basically had to guess, and then test those guesses by booking highly competitive, super expensive time on massive 4-meter and 8-meter ground-based telescopes. They would point these giant telescopes at candidate objects, take a spectrum, and, honestly, most of the time it turned out to be just another ordinary star. It was a really inefficient process with frustratingly low success rates.
So how do we actually fix this bottleneck? Well, enter the SPHEREx satellite. This thing is basically our ultimate near-infrared cosmic magnifying glass. Instead of just taking flat pictures of the sky, SPHEREx uses a special filter to measure the specific spectrum, the continuous rainbow of light, for every single point in the sky across multiple infrared wavelengths. It essentially acts as this massive continuous sorting mechanism that can look past the optical illusions and see the true chemical nature of these cosmic objects.
And the timeline for this mission is moving ridiculously fast. Following its launch in March 2025, SPHEREx is designed to wrap up its very first all-sky survey by early 2026. The researchers whose work we're exploring today simply grabbed this initial data. And looking slightly ahead to late 2026, the satellite will complete its third pass, delivering even higher resolution data. The fact that researchers are already making massive discoveries off just the very first rapid pass shows just how game-changing this continuous wavelength coverage really is.
Now, when you dig into what that SPHEREx data actually looks like, it's pretty amazing. You get these incredibly distinct chemical fingerprints for confirmed distant quasars. The data reveals massive spikes, which are the broad H-alpha emission lines, basically huge bursts of light from hydrogen gas swirling around the black hole. You also get clear, sudden drop-offs in light known as the Lyman alpha continuum break. Ordinary stars in our galaxy simply do not produce a spectrum that looks anything like this. So by analyzing this data, a true quasar reveals itself almost instantly.
Armed with this, the researchers put together what I like to call a highly efficient couch discovery pipeline. Step 1. They used existing data from the Gaia and WISE missions to filter out the obvious junk, like anything that was moving, which proves it's just a nearby star. Step 2. For the candidates left over, they pulled the new SPHEREx spectral data right from the public archive. And Step 3. They literally just sat on their couches, looked at the data on their screens, and visually inspected the spectra for those massive H-alpha spikes we just talked about. No observatory telescope time required. By applying specific color filters to the data, they were able to completely carve away the noise. Imagine a massive, dense cloud of millions of stationary objects recorded by the Gaia mission. That is our cosmic haystack. But using their specific parameters, they isolated their actual quasar targets, pulling them cleanly out of that totally overwhelming background of imposter stars. And honestly, this simple, elegant approach was an absolute breakthrough. By letting SPHEREx do all the heavy lifting of gathering the chemical spectra, the research team completely bypassed the old bottleneck. They didn't have to wait months for observatory telescope time just to see if their candidates were the real deal. The data was already there, publicly available, just waiting for someone to look closely enough. And when they finally did, the results were absolutely staggering. The researchers discovered 87 brand new, incredibly luminous, high-redshift quasars. Literally 87 ancient supermassive black holes that humanity never even knew existed, found simply by sifting through the very first pass of SPHEREx data right from a laptop.
But here is the absolute kicker: 100%. To prove their couch-based method actually held water, the researchers did eventually go to ground-based telescopes to double-check a sample of their new discoveries. And their success rate was totally flawless. Out of the candidates they checked, absolutely every single one of them was confirmed to be a true quasar, a 100% confirmation rate. When you compare that to the historically low success rates astronomers used to deal with, this new method is practically foolproof.
The sheer volume of this cosmic haul is just massive. Beyond those 87 new high-redshift quasars, 19 of which were at the extremely distant redshift of greater than 5, they also successfully recovered 219 previously known quasars, which completely proves the instrument works perfectly on established targets. Plus, they discovered 203 new lower redshift quasars. What's super fascinating here is that many of these lower redshift ones are highly reddened or shrouded in dust, which happens to be the exact type of rare quasar that traditional optical surveys usually miss entirely.
Mapping all these discoveries across the entire sky reveals something really cool. You can see how they even found targets right near the galactic plane of our Milky Way. Now, that's an area traditionally avoided by quasar hunters because it is absolutely packed with those annoying imposter stars we discussed. But with the power of SPHEREx, the researchers were able to confidently peer right to the edges of this tricky region and pull out true quasars that had essentially been hiding in plain sight.
And when we look at the final proof, the follow-up spectra taken from ground-based giants like the Palomar and Keck observatories, every single sharp emission peak lines up perfectly with what the couch-based SPHEREx analysis predicted. The ground-based telescopes acted as the final judge, and the verdict is pretty clear. This accessible, data-driven approach is an unbelievably powerful tool for space discovery.
So, what does this phenomenal success actually mean for the future? Well, it's literally a paradigm shift for how deep space astronomy is conducted. By demonstrating that we can confirm high-redshift quasars with 100% accuracy using continuous infrared sky surveys, we are opening the floodgates. This means way less wasted telescope time, vastly larger catalogs of ancient supermassive black holes, and ultimately a much clearer picture of how galaxies and black holes co-evolved at the very dawn of time. To put into perspective just how far this can take us, SPHEREx is already sensitive enough to clearly detect the chemical signatures of some of the most distant objects known to humanity, quasars with a redshift greater than 5.7. Even in its very first, relatively brief sky survey, it's easily picking up those critical H-alpha lines and Lyman alpha breaks in these incredibly faint, ancient objects. It proves this instrument has the sheer capability to push the boundaries of the known universe.
Which really leaves us with one incredibly exciting thought. Everything we've talked about today was achieved using just the very first quick-release data from this satellite. With 3 more, even deeper, all-sky surveys still to come before the mission finishes, you have to wonder what other incredible mysteries are currently hiding out there in the dark, just waiting for someone to find them from their living room. Thanks for hanging out with me for this explainer, and keep looking up.